Okay, my friends, so let's actually figure out how to take the average of this distribution that we just created, because that's kind of the superpower of probability distributions, is being able to find averages of them. So let's get in here and let's create our distribution. X equals number of rolls, and I'm going to give this a nice little title. I'm going to say roll a die until we get a repeat. And I'm going to be really specific and make sure I say roll a four-sided die. That way people that are looking at our work know exactly what we're talking about. So we're going to roll a four-sided die until we get a repeat. All right, and I'm going to put a probability column over here. We're going to get this formatting done correctly. Give me a sec here. All right. I want to make that stand out a little bit, make it a little bit bolder. Oh, I'm liking the way this is looking. Okay. Now, as far as the number of rolls it could take, we already established that. It's going to be 2, 3, 4, or 5. I don't like the way this looks. I'm going to wrap that text too. I want to center everything because that's me. All right, looking better. Now, the probabilities we just established, right? We just established that it's 25% for 2. So what I'm going to do is I'm just going to type 0.25 for the decimal version of 25%. If you really need to see something in a percent form, type it as a decimal, then convert it to a percent. That's totally fine. I would just rather leave them as decimals. All right, for 3, if I remember correctly, it was 0.375, 37.5% for that one. Now 4, I don't remember the decimal for it, but I do remember, and this I'm actually kind of glad, I remember the fraction. It was 72 over 256, and for some reason those numbers are stuck in my head. And I'm actually glad, because check this out. If you enter a fraction into Excel, you have to enter it with an equal sign. If you don't enter it with an equal sign, it thinks it's some weird formatting like a date or some other strange type of text formatting. So I'm going to type 72 divided by 256, and yeah, 28.125%, which there's no way I would have remembered that. Okay, and then since I'm feeling saucy, I also can't remember the decimal for 5, even though we just calculated it in that last video. I'm going to do, watch this, equals 1 minus the sum of the other 3, which is exactly that cool little thing we did. Yeah, 9.375%. That's exactly right. And if you really want to get fancy, we can actually add up all those probabilities and show that they add up to 1. Now, some of you might be wondering, like, Sean, you know, Mr. Simulation, Mr. F9 button, I'm really surprised you didn't bother writing one of those Monte Carlo simulations to actually figure out these probabilities for us. Well, as it turns out, I did, because I'm a dork, and here it is running right here, a couple thousand trials, and you can see that even with the simulator, you're getting really close to the actual theoretical probabilities that we calculated here. And the reason I like Monte Carlo simulation so much, as I've talked about before, is just because in the real world, what we did here with the theoretical probabilities, honestly, is a little bit fictitious, because you don't get to see the dice, so to speak. You have to observe the behavior, which is what a Monte Carlo simulation does. So I tend to like the Monte Carlos because it's a little bit more realistic to what you're going to see in your daily lives as users of statistics. Now, look at that graph. I'm going to use the graph on the Monte Carlo because it's going to be very similar to the graph from our distribution anyway. And you can see that we've got kind of it's not quite a bell curve. It's bell E, but then it's got this cool tail off to the right. So that tells me a couple things. First of all, it tells us the mode, the most frequently occurring data point, is 3. But it also tells me that the average is going to be a little bit to the right of that mode. Now, how little? We'll get to that in a second. But I can tell it's going to be a little bit to the right because other than that one bar out here, the rest of the curve is pretty symmetric. So that one bar, if you're thinking of average as balancing a tray of cookies, that one bar is going to pull the average a little bit further to the right. But how much further? Well, let's calculate the average now and see. Now, you may have noticed something, that these probability distributions, and I've been talking about this for a couple days, look like grouped data from the statistics world that we looked at before, which is exactly what they are. Instead of this column being frequencies, it's probabilities. So we can treat it mathematically like we did with frequencies. All we've got to do is create another column, which is let's take all the probabilities and multiply them by their data points. So x times p of x, x times p of x. Let's do that now. So take 2 and multiply it by 0.25, which means we see 2 rolls 25% of the time, which means that row right there contributes a half a roll to the average. If I drag that down to the next, that row contributes 1.125 rolls to the average. Drag it again. That roll contributes 1.125 to the average. Drag it again. That contributes about a half of a roll to the average. But what I want to look at right now is how mathematically and mechanically we dealt with that back in the day. Well, if you remember, we added them up. This would have been the x times frequency column back in the day, but now it's the x times p of x column. All right, so now that we've got our table set up in this way, we can proceed just like we did before to find the average. So what we're going to do is we're going to take this value here, which is the sum of all the data, effectively, and divide it by this, which is, well, what used to be the number of data points. But now, this value right here is not the number of data points. It's the total percentage of data points, which as a decimal is equal to 1. Well, if you divide something by 1, you don't change its value, right? Which means that if you have any distribution in tabular form, where you've got all the values of the variable in x and all of the corresponding probabilities in the p of x column, all you've got to do is create one more column, which is the data times its probabilities. Figure out what all those are. Once you've figured out what all these are, you just have to add up all the data times the probability. Don't be scared away by this. It's that big sigma I like to use whenever I can. You're going to add up all the data times the probabilities, and that is going to be your average. You don't have to divide by anything because the division has already been taken care of in the probabilities. That's kind of the benefit of having the probabilities as probabilities. They're out of a hole. So back in the day, when we had to add up, this was a frequency column, we had to add up the frequency column and divide this. We don't have to do that anymore because this column is always going to sum to 1. So there's no reason to have to divide that by 1 because it's not going to change the mathematical value of the average at all. All right, so looking back into our distribution, looking back at what we did earlier, we discovered that the average number of rolls it takes to get a repeated side is 3.2 on a 4-sided die. Now, some of you might be thinking, I don't understand. How can you roll 3.2 times? You can't. You can average 3.2 times. And some of you might be thinking, why does it even matter to have that much precision? Why can't you just say it's 3? Well, to answer that question, I think it's time to move beyond rolling dice with no context and look at some examples where we actually have money changing hands. Let's take a look at 2 right now.